Okay, this is video 7.4, has to do with quantum mechanics. What we've covered up to this point is first off the photoelectric effect, which showed us that light, in addition to being a wave, sort of behaves like a particle and carries discrete amounts of energy. And also that the energy carried by a photon is related to its frequency. We also learned about emission spectra of elements. Because each wavelength of light corresponds to a particular energy, the fact that you have discrete emission spectra for all elements tells us that the electron is only allowed to have certain values of energy. And today we're going to try to explain why. And we're going to start with the Broglie Hypothesis. And this is 1923, so this is 10-15 years after all of the initial work in quantum mechanics. French graduate student Louis de Broglie suggested that electrons might be waves. At this point, it had already been established that light sometimes behaves like a particle, and so he thought, well, maybe it works the other way, if you describe electrons as waves. And the equation he came up with for the de Broglie wavelength is lambda equals h over p, where h is our old friend Planck's constant, which is 6.626 times 10 to the negative 34 joule seconds, and p is the momentum. And we calculate momentum as mass times velocity, remember back to last year. The idea is that the more momentum a particle has, the shorter its wavelength is. So let's first look at the wavelength of an electron moving at 10 to the 5th meters per second. That's 100,000 meters per second, about I think 3% the speed of light. So we just use that equation, lambda equals 6.626 times 10 to the negative 34 joule seconds, divided by the momentum is just mass times velocity. Momentum of the electron is 9.11 times 10 to the negative 31 kilograms, and it's moving at 10 to the 5th meters per second. And we can put that in our calculators. And we get 7 times 10 to the, hold on a second, 7.3 times 10 to the minus 9 meters. So about 7.3 nanometers. Notice that's a much, much shorter wavelength than visible light by about a factor of 100. That's kind of down in the X-ray region. And similar practice, let's ask what the wavelength of a car traveling on the highway is. So mass and velocity, let's say the mass equals 1,000 kilograms. Velocity, 30 meters per second, that's about 65 miles an hour. We're going to get a much, much larger, or much, much smaller number. 1,000 kilograms times 30 meters per second. And we get 2.2 times 10 to the minus 38 meters, which is a very, very, very small number. And think about this a bit, because large objects traveling at normal speeds have very, very short wavelengths, whereas small objects traveling at anything short of very high velocities have longer wavelengths. And so as we talk about quantum mechanics, think about what the effect of that is. Because what that wavelength is has something to do with how much it behaves like a particle versus how much it behaves like a wave. And now we're going to ask, okay, how do we test this? If a particle is a wave, how would we know? And it turns out that it's done basically the same way that light was demonstrated to be a wave, interference patterns. You remember Young's double slit experiment. You shine light through two very narrow slits. You don't see two dots on the wall, you see an interference pattern. You see bright fringes separated by dark fringes. The fact that light is a wave explains that quite nicely. But also, light has a relatively long wavelength compared to what we just calculated for an electron. And that means that the slits can be cut, a millimeter apart, use red light, and you'll get a visible interference pattern. But if the wavelength of the electrons is typically 100 times smaller than that, then that means the slits need to be very, very, very close together. Difficult to make with photographic etching equipment. So what we need is a very, very small distance between two sources. And they thought this up, I think this was sometime in the late 20s, that if you shoot an electron beam at a crystal, the atoms in the crystal act like sources. So the idea is that you have the atoms in the crystal, and they're regularly spaced. And then you have electrons coming in like that. The electrons will bounce off of this atom, this atom, this atom, and like so. So the electrons are, they're not all in a line like that. And so they'll reflect. And so you have a large number of sources at a regular spacing d. And if electrons are in fact waves, we expect to see an interference pattern. That is in fact what they found. The general setup, this is called the Davison-Germer experiment, you need to be able to explain it on the IB exam, is that you take those electrons, you shoot them at a crystal. For the particular crystal that they used originally, the distance between the crystal planes was 4 angstroms. Angstrom is a unit of length that's equal to 10 to the minus 10 meters, or a tenth of a nanometer. Oh, and I'm sorry, they didn't use they did use electrons. You can also do this with neutrons, it's just a little more difficult. And then you make sure your detector is at the same angle as the incoming beam, and then you're going to make a graph of the number of electrons detected, so the number of electrons that reach the detector, corresponds to the brightness of the light in the wave, and we graph that versus the angle theta. The classical hypothesis says that all of the electrons should bounce off roughly at the same angle, and that the reflection angle will be the same as the incident angle. So classically, what you'd expect to see, the number of the electrons versus the angle, you'd expect this to be more or less constant. You'd see small fluctuations, you'd probably see a bit of a drop off at high angles as the electrons go into the crystal, but you'd see more or less a flat line. That is not, in fact, what they saw. What Davison and Germer actually found was that the graph had a peak in it. So we plot n versus theta, and it looked kind of like that. They found a peak at about 50 degrees, and they saw what appeared to be the beginnings of another peak, but once theta got to 90 degrees, they couldn't take any more data. So that peak there is an interference pattern. So they could show that electrons could interfere with each other, which is odd, and thus that at certain angles they don't actually reflect from the surface. Essentially, this is Young's double slit experiment applied to electrons. The other thing they found is that if you vary the energy of the electrons, which is to say you change their momentum, you can move the angle, the maximum scattering angle, which implies the wavelength does in fact depend on momentum. And in fact, they confirmed Broglie's hypothesis that the wavelength of the electrons is equal to h over p. Wavelength depends on, not determines. So that is the basics of why light is a wave. You need to be able to apply the equation and state de Broglie's hypothesis, and most importantly, you need to be able to explain the basics of the Davison-Germer experiment on the test, because they're quite likely to ask you about that. Next time we'll look at some of the consequences of particles actually being like waves.